We've already talked about electronegativity before, but we haven't really defined it. We've talked about it when we were talking about the trends. When you look at trends in electronegativity, these are numbers that actually correlate to actual electronegativity. And you can tell that it increases in this direction and it increases going up, making fluorine the most electronegative point on the atom. So right there, notice that there are no noble gases on this chart. That's kind of a thing. Notice that the highest value is 4 and the smallest value so far is, that 0.7. Generally speaking, we say that the scale goes from 0 to 4, where this is the most electronegative. So this was kind of all covered over in the section where we were talking about trends, because it's like mini trends in that it heads in that direction for increasing. So what is electronegativity? Let's take a look at electronegativity and let's see what it means to us. So there are kind of two types of bondings we've kind of talked about, or we will be talking about. This is sharing bonding. So when we draw a line, and I put 2 dots on it. You don't normally put 2 dots on it, but we're about to show what those electrons are doing. When they're sharing this way, then this is the covalent bonding. When they have actually when they've actually given electrons to someone else, that's ionic bonding. There's actually a case in between the two. It's a type of covalent bonding. This is pure covalent. This is type where we say that it is polar. We're going into that word in just a second. But basically what it's saying is that if we look at this one on this side, it's kind of like saying you've got a pair of twins that have a tug-of-war rope between them. They've worked out exactly the same and they're pulling equally. And that flag in the middle, it's not any closer to either one of them. When you look at this one right here, what it means is maybe we've got like a great big 5th grader and a tiny 3rd grader, and they're on the rope. The 3rd grader hasn't let go, so it's still feeling the bond, and it's still sensing these electrons, which is important. But the chlorine basically is attracting these electrons. Maybe he's offering them money, or there are reasons behind this, but it's not in Gen Chem 2 so much. But it is grabbing these electrons and pulling them. So all this electron density is all sitting on here, and the hydrogen doesn't have very much. This is electronegativity. It's how strongly the atoms can attract bonding electrons. So in this case, this chlorine can attract it really well, but the hydrogen can't. In this case, it doesn't matter because it's the same atom, so they both are attracting equally. In this case, the chlorine is so much stronger than the sodium that the chlorine has not only attracted the electron, but he's actually pulled it off, and now these two atoms have a completely different kind of bonding. They're doing ionic bonding, and it's based on this electrostatic difference. And you might be thinking, well, why do we care? Why do we care? Well, it's because there's a cumulative effect. And I know this probably seems so picky when we're talking about where are itty-bitty electrons in an itty-bitty bond. But there's a cumulative effect, and it is huge. It explains so many things about atoms. And you want to think of maybe if you have a pile, remember we talked about Avogadro's number? That number of atoms might be like holding a piece of charcoal in your hand. That's 6.022 times 10 to the 23rd. That's how many it just is in a piece of charcoal. So the atoms in that number of atoms, they begin to line up like magnets. Versus just like a big old pile of dominoes, they don't. Now, in the case of like a charcoal piece, it's actually a pure bond, and so it would be much more like the dominoes. But if you had other elements, they're going to line up with this kind of a bonding. So the way we represent that when we're drawing it is, there's two actually different ways that we can do it. Is that you can use a delta, and I'm sorry, but my deltas look awful. So use your own delta. And in this case, there is no difference, so we don't write anything. But over here on the right, since there's a little bit of a difference, I'm going to go and erase a little bit to make it a little bit easier to see. I keep erasing too much. We would put, this is where the electrons are over here, and so it actually kind of sort of makes a little kind of sort of negative. It's not like a fully negative thing, but it's enough. So it's, we call this partially negative, and then this is partially positive. It doesn't mean half, it just means it's more negative on one side and more positive on the other. So those are deltas, and that's one way we represent it, is we just put those above the bond like that. Another way, and I like this way even better, is we'll use a little arrow. And the little arrow, we start it on the positive side, that's the hydrogen, right? Because he doesn't have much. And we will draw like a plus sign, just like a positive, but turn it into an arrow where the arrow points at the negative side. And in fact, I often, and you'll see this too, you'll actually put it on top of the bond itself. The carbon can go back up, but you'll actually write it on top of the bond when you do this. So that's how you draw these atoms. Having issues here getting these to stay still.